Good evening. I just wanted to check in.
Good evening, Professor Lohan. Hi, can you hear me?
Yes, I can hear you well. Acoustics are good?
Yeah, everything's so good so far. You can share your screen if you want to take a try.
Sure.
Okay, we can see your screen clearly. And we will be starting at 9, and 9 in China.
Yes, perfect. Okay.
Okay, see you then.
See you then.
喂，我这边应该是好的吧？
喂，袁老师，可以听到你。
好的，我试一下摄像头应该。
可以看到。
好的。 Hello, Professor.
Good evening.
Yeah, I'm Jimin, today's host. So you have tried your slides. It works well, right?
I think it's all working well.
All right, perfect. Okay, I think, yeah, it's time to start now. So hello, everyone. Welcome to EEH Talk tonight. I'm today's host, Jinbin. Today we are very pleased to invite Dr. Professor Rena Lohmann from University of Rhode Island University. Yeah. I think it's the second time you give us a talk, right? Yeah.
It's great. Sorry, I just had to take care of a ringing telephone, all taken care of.
Yeah, it's very good. So before the start, let me introduce Dr. Rena Lohmann. So Dr. Rena Lohmann is a professor at the University of Rhode Island Graduate School of Oceanography. He has a degree in chemical engineering and a doctorate in environmental science. He is the director of a URL-led Superfund Research Program Center on the sources, transport, exposure, and effects of PFAS. His research focused on the detection, fate, and the transport of aerophonic pollutants in the environment, often relying on passive samplers in the process. And today, his topic is about the novel passive sampling detection tools for PFAS in water and air. So please, Dr. Rena Lohmann.
Thank you very much, and a good evening to all of you. Let me share my screen. All right, so thank you very much for the introduction. Again, a very good evening to you all in China. Sorry that it's a late hour, but I understand it's recorded, so people don't want to be up at 9 o'clock in the evening. Maybe they can enjoy it for breakfast. All right, so I'll talk a little bit about PFAS and then how we think we and others, I mean, it's as a bigger community that's developing sampling approaches for PFAS in air and in water. And then I'll finish with some thoughts. So PFAS, certainly in the United States, but I've seen plenty of studies from China, plenty of studies from Europe. So it's clearly not just a problem in the US. In the US alone, we're talking hundreds of contaminated sites. The contamination is particularly well known for those PFAS where they've been used in firefighting forms, so military sites, airports, and fire training areas. And then, of course, there are some other sites that are particularly high because that's where PFAS were used in the production of fluoropolymers, of other PFAS, and in manufacturing. And I think I've seen similar studies from China that near industrial production sites, you have very, very high concentration of PFAS. They are mostly used in production of Teflon, so fluoropolymers, like you would find on outdoor gear, like rain jackets or the famous Teflon frying pans. And of course, by now they've contaminated the drinking water of millions of people in the US, in Europe, in China, across other parts of the world. We also know now, and we come back to that in a few minutes, that they cause a wide range of effects. Of course, we particularly are interested in the effects on humans, but a lot of the studies are done on animals. And some of the human epidemiological studies show that particularly the exposure to PFOA, one of the main compounds of concern, is linked to changes to metabolism, being overweight, obesity, and changes to insulin concentrations in the human blood. Of course, as we know, they are very different because they are charged, they bind to proteins, and in the US, PFOS is not produced anymore. P4 has been phased out, and some other chemistry has been replacing PFOA. Now, this would have been a very normal talk, except that only a few weeks ago, the US Environmental Protection Agency came out with an interim health advisory. And it's only an advisory, so it's not binding, but it was very shocking because basically what the EPA decided is that at this moment in time, there is no safe level for PFOA or PFOS in drinking water. And the concentration they advise as being safe is lower than our current detection limits. So basically they're saying that no amount is safe. And now this is a health advisory, so it will not become law as is, but it is a striking departure to previous advisories from the EPA that were initially at 400 parts per trillion, then it was at 70, and now it's 0.02 or 0.004. The health advisories for Gen X were a little higher at 10 parts per trillion and quite a bit higher for PFBS at 2000. So they're still in the right range, but of course PFOA and PFOS, typically the most widely found, and their concentration, the advisory is very, very, very low. So within my research center, we look at a wide range of science linked to PFAS, that is from the fate in the groundwater and bioaccumulation to the effects on the immune system in children. That's one of those studies from Philippe Grandjean was used in the EPA's health advisory to look at the toxicology of PFAS and their detection tools. The center also has a training course for graduate students and postdocs, research translation to work with some of our stakeholders in federal or state agencies. We work with the community near a contaminated drinking water site from fire training and military use, and we have an administrative core. So as most of us, of course, are fully aware, chemicals that are very persistent, so they don't break down easily. Basically, you'll find it any and everywhere in the environment because they don't just go away. So even though they are produced and used in industry, they end up in consumer products, either on purpose or accidentally. And then we get our exposure as humans through all kinds of food, drinking water, but also dust, air. And of course, they cycle through the environment, be that through the waste we produce, through the water and the environment that contaminated, and then it gets back into agricultural, so food items, and then of course, we're eating those again. So we have this complex exposure. And as an example, shows a couple of studies here from Washington, from the US, and Chen from China. And the one on the left shows the spread of novel PFAS, chloroperfluoropolyether carboxylates, in and around New Jersey. And it turns out the concentration in soils can only explain if these chemicals that are charged are transported through the atmosphere. And on the right-hand side, study by Chen et al., looking at the distribution of PFAS away from a fluoropolymer manufacturing plant. And again, you see the potential pathways show atmospheric pathway as well as surface water, groundwater, and so on. So we have to live with both pathways these days. And that is a new insight because initially we thought they would all be waterborne and water transported. And of course, this also is reflected in the exposure. So again, this is a study from Chen et al. Hubei is a manufacturing plant for fluoropolymers, and Ziyang, excuse my poor pronunciation, is a place where consumer products are used. You see, of course, a much, much greater exposure at Hubei in red for various sulfonates and carboxylic acids. And then if you look at the relative exposure pathways, you see anything from being dominated by vegetables, so uptake of the PFAS either from the atmosphere or through groundwater. You see exposure through fish, which we assume for the longer chain acids, very typical. But you also see the importance of cereals or legumes, eggs. So anything and everything is a very complex exposure, and that makes it very difficult to regulate effectively if you want to protect human health. So with that, let's just take a little bit into the passive sampling world. Passive samplers are very interesting tools because they really are reflective of the chemical activity of a pollutant, or Kevin Jones would have said the fugacity. And that means they really reflect the compounds that are either dissolved or in the gas phase. And the uptake typically is only by diffusion. So what happens over time is shown on this plot here, uptake in a sampler over time. You have initially something that's the linear uptake, and then it starts to approach equilibrium, and then you have some equilibrium part. And you can really use a passive sampler in either of those two phases. And if you do it early on, it's the linear uptake, that's here. The only thing you really need to know is what is the volume of water air sampled per time. So that's the sampling rate. If you wait long enough, you get into the flattening out part, the equilibrium part, and now you need to know the equilibrium partitioning constant. And of course, you have to know this at the right temperature and potentially salinity if you work in the marine environment. So you have to work between those two different phases. And if you work in the linear uptake phase, you have an added advantage. The sampler more or less reflects a time-weighted average of the concentration surrounding it. So you get a representative concentration. Why would we do passive sampling? I mean, it really depends. For hydrophobic chemicals, PCBs, dioxins, DDTs, we often cannot easily measure them in the dissolved phase. Concentration are often too low because they're hydrophobic, and then we use a passive sampler that might be a polyethylene sheet, POCUS, or a silicone to enrich it, and so basically overcome our detection limits and get a measurement that otherwise we cannot get. You can also use it to come up with a pore water concentration, which otherwise, again, we cannot measure easily. Now, PFAS are a little different because they're ionic, and we can analyze them by LCMS, and the detection limits are very low. And typically for PFAS, if you just take a water sample of a half liter or a liter, you can measure that easily. But of course, you only have a snapshot in time. So again, the way of getting a representative sample is something very powerful. The other thing that is shown here in a study by Cerveni et al., looking at concentration of PFAS in liver of different fish along the Danube, and then looking at the concentration of PFAS in a passive sample, in this case a POCUS, you see they're very similar profiles. So it's a good proxy for availability by availability. And of course, the question is the air actually important? And so there's one study from McKay from Canada that showed, and this is an unusual way of displaying the data, so let me quickly explain. Here's the concentration of PFAS, or alkyl acids, in the serum, so in the mothers. And here are shown concentration of two precursor chemicals in tiers, lowest tier, middle tier, highest tier, in the atmosphere in the houses. And in both cases, for both precursors, the higher the concentration in the indoor air in the house, the higher the concentration in the mother's serum. And if we look at two acids, we see the very two similar stories. So, of course, this is not conclusive evidence, but it's very strong, suggestive that indoor exposure matters for uptake and concentrations. And of course, it's these concentrations that drive the health risk and the adverse effects that we are worried about. So basically, air seems to matter. And because of that, there have been a few studies, not a lot, but a few, that try to understand what are the concentration of PFAS in air. And this is one by Lutz Ahrens almost 10 years ago, where you see the classical high volume air sampler. So the one with a pump and power, very noisy. And then you see a wide range of passive samplers. These are in stainless steel bowls, the typical polyurethane foam disc that Environment Canada uses. And what you see in these graphs is now the black spikes are weekly samples of different PFASs. And then you see different passive samples as a comparison. And you can nicely see, let's say here, let's take PFOA, the environmental concentration go up, so do the passive sample concentration, the straight lines. And so the passive sampler takes an average concentration, reflects what is measured through snapshot samples. So if you want to know an average typical concentration, you really want to go with the red because you have far fewer samples to take. And of course, it's always there, even though when you're not having your high vol sampler turned on. One thing that turned out to be a problem for PFAS is that the polyurethane foam itself does not retain enough PFAS, and you actually start equilibrating them very quickly. That's shown in the bottom graph here. And the way the GAPS program was set up, they always wanted to be in the linear uptake phase. So what the group did then in Environment Canada is to add small sorbent particles to the puff to come up with a sorbent impregnated puff disc or SIP disc. And with that, that's shown on the right, you get a much longer linear uptake phase, and that's what's typically used by Environment Canada that operates for months. So there's one sampler. The problem is it is not easily commercially available. We chose a slightly different approach. You see the same stainless steel boards. We use polyethylene sheets. A few years ago, we tried to let them equilibrate with a master student of mine, Eric Dixon Anderson, and we noticed that after a week or so, basically almost all chemicals seem to equilibrate within the passive sampler, but these were only the precursors. We follow up with this concept, and you still see again our polyethylene sheets. This is now indoor air. This is Maya Morales McDavid. Same idea. Can we use them as indoor air samplers? Did a study of uptake over time. 4 days is basically equilibrium. So we typically now wait for a week or a little longer to make sure. But so main concentration, sorry, main message, indoor air concentrations, we can measure, they equilibrate fast, and we can get detection. So we use that and compared it to an active sampling approach. We use small disks, derived our partitioning constants, and now we're able to use the polyethylene sheets as passive samplers. So we went to a wide range of settings. These are kindergartens from California, some samples on my campus in Rhode Island, and we went to an outdoor clothing store. So the outdoor clothing store was actually our field testing site. We knew outdoor clothing is typically impregnated with PFAS. So we used that as our test study to make sure everything worked. And you see, with exception of one sample, everything else looked pretty much the same. So this was our, and particularly if we used a slightly thicker polyethylene sheet. So this showed us there is constant background is high. University of Rhode Island, very mixed results. We have some offices that were basically totally clean, others that have very high concentrations. So we think this tells us, A, that there are point sources that are very important, and these are likely consumer products, could be just clothes. It's not just the building materials, even though that probably also plays a role. And then in the kindergartens, again, we see a wide range of concentrations. These were mostly not carpeted. We know carpets play a big role, but so we think the culprit here is not the carpets. It's probably, again, consumer products. Maybe, depending on when they were renovated, some of the materials used indoors. We then look at how does that affect the uptake by humans, and turns out the red bars is the contribution of the precursors, the volatile precursors in the air, and the black, and the black down here would be the dust. That most of the time the gas phase is important for the volatile fluorotelomers, and the dust becomes important for the heavier precursors, so like the focis and fossils. If we look at other studies, and in this case I use something from Europe, it's similar that the fluorotelmer alcohols are much more abundant than the other precursors. So that hasn't changed, even though the chemistry of the precursors should have changed, because the 8,2-F2H should have been phased out in the early 2000s, and that, or 2010, as part of the phasing out of PFOA, the 8,2-F2H should have also been phased out. The contribution to the daily intake of the PFAS of these precursors is typically low. So that really means they should be safe. So the European Food Safety Agency set the tolerable daily intake at 0.6 nanograms per kilogram a day. And you see these units here are much, much lower than 0.6. So in the big scheme in Europe, we think food, particularly fish, is the main exposure pathway. So everything should be safe. Of course, the most recent health advisory by the EPA really changes all of this. the reference dose is set now so low that basically just living inside a normal home will already put you at or above the safe environmental uptake. So this will require a lot of thinking and work, how to communicate this and how to enforce or what to do about if you indeed stick to a health advisory that is so low. All right, so with that, there are some tools that exist for PFAS in air. It was not initially thought to be an important pathway. We now know it certainly is an exposure pathway. Carpets are typically the most worrisome material that we know of inside homes, but of course some of the results show that exposure is very scattered, and that probably has to do with point sources and consumer products that we don't quite know what really they are. And a lot of work will have to be done, particularly in the US, if we stick to these really low exposure guidelines. But we continue to really want to find more convenient detection tools to identify the sources and of course what to do about it. So with that, let's go on to the water side. And of course on the water side, it's a longer established problem, and there are more different tools out there. There's the ChemCatcher, the POCUS from the United States Geological Survey, and of course the whole DGT approach championed by Kevin Jones's group in Lancaster. And Chang'e Chen might be on this call, I might see you later. And of course, he has been working a lot on the DGT approach. So the POCUS, shown here on the bottom left, is sandwiched sorbent between two membranes, and they are protected by big stainless steel discs, and then have a safe container for deployment. And you see on the top left how, again, if you deploy it long enough, you reach some equilibrium value. But for the time being, this is a study by Sarit Kazazon from Australia, looking at various PFAS in groundwater contaminated by AFFF and deploying POCUS. And you see that you have a nice steady exposure. You see how the sampler starts to equilibrate, and you can use that to derive the sampling rates. And you can compare then the concentration from the passive sampler to the grab samples, and it's almost a one-to-one line. So this tool seems to work. Now this was deployed in groundwater, and groundwater is very slow moving, so the uptake rates are very low, talking about sampling rates of 100, 200 milliliters per day. The DGT is a very different approach. Again, it was championed by the group in Lancaster, Richard Davison, and it has a diffusive gel. So there's a known thickness of a gel through which diffusion will happen, and then it has a receiving gel in which the compounds of interest are bound, and there's typically a filter in front. And it's really the thickness of this diffusive gel that determines how long it takes for the compounds to move through. And what you need to know to make this DGT work is you need to know the thickness exactly, and then you need the diffusion coefficient in that diffusive gel as a function of temperature. And with that, you can deploy for a known length of time, and then you can back calculate what the concentration was outside. So it's a very interesting approach. And because the thickness of the diffusive layer should be fairly thick, it removes any effects of the water flow outside of the DGT. So this is the first study that I found for PFAS from Guan et al. More recently, Yang et al. Published work on PFAS in the Journal of Environmental Science, so there's more work coming out. This is work by Jonathan Charlie et al. 2021, showing the calibration of different PFAS and two different gels for the DGT sampler. And then this was shown at two study sites, one in Guangzhou and one in Foshan. What you always see here is the direct measurement of water through grab sampling in white, work well for PFBS, work well for PFOA, work well for PFNA, but some trouble with PFOS. And on the other side, same story. It worked well for everything but PFOS, which might just mean that something didn't work out with the calibration. But basically the concept is there. there's more and more studies showing that this is one way of measuring PFAS in water or pore water. Another approach, and that's again Sarikazazon from Australia, and we work with them. So we have some experience with this particular sampling approach. It's shown here. It's a small tube sampler. It has caps on either end, and it's a porous tube. And again, you see the validation in groundwater, steady linear uptake over time. This goes for 3 months. And from these linear plots over time, you can derive again the sampling rates. And these are shown here. And these are very low. So these are a few milliliters per day. So much, much lower than we had seen earlier for POCUS. But of course, this is groundwater. Concentrations are high. So the benefit you get from deploying a sampler like this in groundwater is that you would get a time-weighted average. And of course, those of us who work in groundwater say, well, groundwater concentration doesn't change much, but we of course know that if there's a rain event or a long drought, that concentration do fluctuate due to other outside circumstances. So it's actually not a bad idea to have a tool that really gives you an average concentration. And again, here is a plot showing concentration by active versus passive. And again, you get a fairly good one-to-one line between the different sites. So it seems again that these samples are able of reproducing environmental concentration rather well. We took those same samplers, Christine Gardner, a student of mine here with 2 colleagues from the EPA, and worked with them in surface water, so in Narragansett Bay. We used 2 different deployment methods, either without protection or with protection, and we basically get the same results. So they work well in the environment, roughly within 20% variability, which we can live with, I think, for PFAS. And so then we did some calibration in a wastewater treatment plant effluent, Fields Point here. Concentration in the effluent are pretty stable over time. We used those to derive the uptake rates shown here for 9 of the chemicals. And again, they're fairly linear over time, so we can work with those. We did a simultaneous test deployment at another treatment plant, the effluent, and shown here is the concentration derived from the passive sampler we used. And here the concentration we measured from daily composite samples. And basically, for most chemicals, we're doing pretty fine. The exception down here is PFAS. Typically, we're in one-to-one line. We have, I think we're slightly over-predicting, but we're certainly within 50%. So we think this is a decent approach to measure dissolved concentrations. The one thing we noticed is that the sampling rate actually does vary depending on how long you deploy them. Initially, it's much higher. These are the dotted lines. And then as you get it to 1 week, 2 weeks, or 4 week deployments, these are the bars in blue, yellow, or black. You get much lower and more reproducible sampling rates of around 20 to 30 milliliters a day. And that's typically what we now use in surface water. We do some follow-up work with these samplers because we're interested in better understanding this effect of water flow on the sampler. So we have an experimental tank where we deploy them, as shown here. We change this speed with the water moves to understand the uptake dynamics. The other thing we've tried is working with colleagues at Brown and use something else. We use nanographene. So this is Bob Hurt from Brown University. He has been helping us come up with these chemistries here. So they start with a graphene oxide suspension, turn it into a nano sampler here, pretty small, has a very high surface area, and it's actually mostly water, 96% water, a little bit of graphene and plenty of water to move things around quickly. So it's like a hydrogel. And I did some chemistry. And so we realized the surface area is very high. And so that gives us plenty of adsorption capacity for the sampler. Now it turns out this particular sampler has one problem. So it a typical pH, the sampler is negatively charged. And if we want to sample PFAS, it repulses it, as it's not attractive for PFAS to end up on the sampler. So the Brown group then basically added this diammonium group to add functional groups on the surface of the nanographene to get a positive charge. And so this is the modified. It has now this aminobenzylamine group and the NH3 plus group. So now has a positive charge, and that's of course much more attractive to all the negatively charged PFASs. So this is our reworked, modified nanographene. And so we did a couple of studies. You always see two bars here for a wide range of PFASs. One on the right is the nanographene as is, and on the left is the chemically modified. And you see that basically we increased the absorption by an order of magnitude or even more. Only for the very long chain chemicals is there no difference, because they are so hydrophobic that they don't really care about the charge anymore. So we get much better attraction of the carboxylic acids, order of magnitude better for the sulfonic acids, do a little bit better for most precursors, or we do as well. We do a little better for Gen X, and we do better for the sulfonates. So this is the chemically modified nanographene. And then lastly, we did it in the field. We employed it in New Jersey, in the Delaware River. You see in the top, you see PFAS concentration in water from grab samples. And the bottom, you see concentration of PFAS in water derived from the graphene monolith, so the passive sampler. So there's a good news story and the bad news story. The good news story is the profiles are pretty much the same. These are mostly long chain PFASs, a couple of precursors. The bad story is that we're not doing well in getting the concentrations right. So here they are at around 40 nanograms per liter. We only report 8. And we think for the first time we had a problem with competition. And so our follow-on work is to improve how we use this particular nanographene. Lastly, this is in work. Yeah. We're also trying to figure out a way of measuring PFASs in pore water through a fiber. So it's just like a SPME fiber. And we have the partitioning constants. That works pretty well. We still have to work on knowing the effects of different exposure lengths and exposure types. But that would help us go into sediments or soil. So with that, let me take a look at what we've been trying to do. So we really want some better idea of the presence of PFASs over space and time. And we think passives can be very useful for this tool, particularly if you want to get a good idea of representative concentration across space or at different sites. We think then passives can be very useful. So far, most of the samples that have been used are working in the linear uptake phase. And so we have tried to play around and develop whether we can use some that equilibrate. And the equilibrium part has been very successful for non-ionic chemicals, but we're trying to figure out whether there's a benefit to having an equilibrium sampler for PFAS, like the nanographene or the SPME fibers. For everything else, the time for linear uptake is really important, just like it is for the POCUS or the DGTs or the tubes. So how long can we deploy them? What is the reasonable time? Doesn't matter if the sampling rate is low. So do we just have to do longer deployment times, or our detection limit is good enough? So those are some of the questions we play around with as we work further on detection tools. So with that, I think we can say by now that we have a small range of passive samplers. They're certainly working for air. We're trying to get a little better at measuring this gas phase. We do a little better on the water side because there have already been some established principles through the DGTs, the POCUS. There's not as much development on pore water samplers, and yet to come is the link between to have a passive that is actually proxy for bioaccumulation. That has been very powerful for PCBs, pHs. We're not there yet for PFAS. And of course, then as I started at the very beginning, we have a complex exposure. So we have both what's in the house, air, dust, products, what is coming through exposure from the field, food web contamination, and understanding both of them is very difficult. We also have, of course, and I didn't touch on that very much, too many PFAS out there. We have suspects, we have unknowns. So there's a lot to be learned. The number of PFAS is a little too high, but we probably still have to think we should be able to figure out hundreds of PFAS. Right now, most good laboratories, 40, 50. So there's still plenty of unknowns that we have to realize what they are. So which of course has led many for us to think we should think of them as a group and use approaches that measure the total PFAS is extractable or total organofluorine. So we have some idea what's out there, whether we're missing a lot. So with that, thank you very much, of course, for your attention, some of the funding agencies for us. And of course, if people are still awake at this late hour, I'd be happy to take any questions.
Right. Thank you very much, Professor Lohmann. I think all of us learned a lot from your speech, and including the pollution, the abundance of PFAS in various environments, and of course, the most important, the detection of PFAS. You introduced a lot of passive samplers for PFAS detection. So now is the Q&A time. So if any of you have any questions, just leave your message in the chat window, and or you can press the hand button and we can unmute you. So Professor, I'm curious about the standard of PFAS. We have seen that EPA have given a very strict standard of PFAS. It is at the PPT level. I'm curious, how is this standard made? That it made by some kind of in vitro or in vivo experiments or some other experiments for that? Yeah.
Yeah, it's a good question. Traditionally, EPA has relied on animal testing, and then they use factors to account for the differences between rodents and rats or mice and humans. Now, the particular standard that the health advisory was actually based on human data. And the authors of the human data, which is the immune system development in children, came up with slightly different, higher safe doses. What EPA did is to again use an uncertainty factor of 10 to say, we did these studies on young children in Denmark, but humans are very diverse. So we put a factor of 10 uncertainty for different genetic makeups, basically. So that's how you end up with really, really low levels suddenly, much lower than anything we've ever thought would be achievable. So yeah, it's a mix of, typically it's a mix of animal data or human data. In this case, the human data was the most sensitive.
Yeah. All right, thank you. So we now all know that the passive samplers is very important for PFAS detection. So there have been a lot of passive samplers. These samplers are specifically for PFAS during the collection, or it collects all of other substances in the environment. So I mean, is the specific very important for PFAS detection, or is not?
Very good question. So almost everything I've shown is not specific to PFAS. Any ionic chemical, any neutral would work the same way, would be attracted and bound to the sampler the same way. I think there are a couple of unique features. For a lot of the other chemicals, the samplers I've shown would not be enough to overcome detection limits because the LCMS for PFAS is very sensitive. And the other part, and I actually haven't shown it, but I know there is a new sorbent out there, Dexsorb, and that is particularly targeted for PFAS, having a certain pocket that more or less fits. But again, it would work for any charged molecule. So now, if you have the right conditions, the right LC, the right setup, you could analyze a wide range of chemicals. Absolutely.
Thank you. Oh, I see the audience want to talk with you. Okay. So Dr. Jiang Chao, please.
Yeah, hi. Yeah, yeah, is it going through? Okay. Thanks a lot for the talk. So we are interested in doing like sampling at individual level. So I see there are many devices and the different materials being used in your talk, since I'm from sort of a microbiology sort of exposure background, and am recently becoming interested in the monitoring chemical exposures, and probably the most familiar device I know is from the Dr. Crystal Pollitt at the Yale University, the fresh air wristband. So I was wondering, comparing to that device is definitely smaller, and I think using PDMS materials. What's the difference between like the device you showed using the polyethylene PE sheets, or between these two materials in terms of monitoring the air exposures? Thank you.
Of course, yeah. So the wristbands, of course, have become very useful to assess individual exposure, and particularly as you walk through your daily life. I think our more to put a sample in a given room or location to know better the concentration in that room. Maybe a combination of both is what we actually need. But yeah, so back to the chemistry question. I think we've seen that silicone is a better polymer to attract a wide range of chemicals, be that hydrophobic or slightly polar. Silicone is not as good if it comes to ionic chemicals. So that's why a lot of this, so I didn't go into the details, sorry, a lot of the solvents we use are either the HIB or the wax, so hydrophobic lipophilic balance, or the weak ion exchange. So they're typically slightly different makeup. If you're just interested in the precursor chemicals, the PFASs, then silicone should work just fine. Same as polyethylene. They both have decent affinity for neutral chemicals. So in this case, either should work. Yeah. The polyethylene is not great because the affinity for fluorinated chemicals is not that high. So the equilibrium partitioning constants are not as high. I think the same would hold for the silicone. So you can probably make it work because often in the rare concentrations are high enough. But if you're very interested in that, you should probably find a different solvent, would be my suggestion.
Okay, thanks a lot. Thanks a lot.
All right. If any of you have any questions, just leave your message and we can see you. So I have another question on the detection of PFAS. Besides the passive samplers, is there any progress on the quick detection of PFAS, like the in-field sensor of PFAS in water or air? Yeah. Yeah,
the Holy Grail, yes. There are certainly studies that try to do a in situ straightaway sensing. Everything I've seen only works at pretty high concentrations. And that, of course, puts us in a strange position, because if the concentration is really high, you can, of course, take a water sample, put it straight in the LC and get a number. And that is probably just as useful. So I know there have been tests of sensing PFAS directly, but I fear we've already probably identified most sites that are heavily contaminated.
Yeah.
So I'm not sure it's going to be that useful going down, because now we're starting more and more interested in detecting reliably low concentrations.
Yeah.
But yeah, I wish, I mean, of course, that would be the best thing you have, a little handheld device, go to the field, get a yes or a no. I don't think we're there yet, and I'm not sure we'll ever be, because concentrations are so low now that we want to or need to detect.
Yeah. That's difficult and needs more investigation on that. Yeah. So let me see if there are any questions now. So if not, I think, yeah, it's time now. Yeah, okay. So thank you, Professor Lohmann. Thank you for the wonderful talk today. Hope you have a good day today. And thank you everyone for joining us. Yeah.
Well, thanks for tuning in at this late hour. Hope everybody stays well. And I'm sure I'll see you at some other EEH talk. Have a good night, everybody.
Thank you. See you next time.
Bye-bye.
Bye.